Hey everyone, how's it going? In this video, we're going to take a bit of a break from looking at the messenger molecule signaling pathways, and instead, we're going to look at the process of different messenger molecules binding to receptors to produce responses. And we're going to look at things called affinity, efficacy, and potency, and also dose-response curves. Now, these concepts may be new to you and they may seem a bit confusing at first, but don't worry, we're going to break it down nice and slow, go through things one at a time, and explore things at a more surface level rather than really in depth. Let's get into it. So, you guys are probably familiar with this first concept. We've explored it in past videos. Basically, your body makes messenger molecules. Messenger molecules are very important because they go and bind to receptors to produce responses. Messenger molecules are also known as agonists or ligands, and they go and bind onto receptors that are either found on cells, so on the cell membrane, or inside cells, so floating in the cytoplasm. And when it goes and binds to these receptors, different responses can occur. And the way that these responses happen is because when the messenger molecule goes and binds to these receptors, certain things can happen inside the cell. For example, second messengers such as cAMP can get activated, or ion channels can open, either letting ions into the cell or out of the cell. Or proteins can be genetically transcribed and translated. So these are some different ways that responses are produced. But it's the binding of your messenger molecule or your agonist or your ligand, the binding of it to your receptor that triggers these processes and therefore produces a response. So now we've covered agonists and ligands, which are different terms for messenger molecules, right? But the cool thing is that pharmaceutical companies, so medicine, drug companies, they can make artificial drugs that mimic the natural agonists that our body makes. So these drugs can produce desired responses. They can go and bind onto receptors, just like our body's natural agonists, and they can produce responses inside our cells. And these responses can be desired. They can help our body fight diseases and conditions, and that's how drugs and medicines can help us. So this now leads to two different types of agonists. You have endogenous messenger molecules and exogenous messenger molecules. Endogenous, you can remember the two letters En. N sounds kind of like in, so you can remember that it comes from inside the body, naturally made inside the body, whereas exogenous molecules, they come from outside the body, so they're artificial, man-made. They usually are drugs or medicine. They come from outside the body, but just like endogenous messenger molecules, exogenous messenger molecules, they act in the same way. They can go and bind onto receptors and produce various responses. Now the cool thing is that pharmaceutical companies that are designing these exogenous drugs, they can make little tweaks so that they produce perfectly desired responses. So they can make exogenous versions of endogenous drugs that are maybe slightly stronger or slightly weaker, depending on what the desired response is. And this way they can fight diseases and conditions as effectively as possible. So, for example, right, our body naturally produces histamine. So histamine is an endogenous messenger molecule. Now histamine can go and bind onto different receptors, such as your H2 receptors, to produce the response of releasing gastric acid. Now let's say we have an exogenous messenger molecule called bistabine. So this is exogenous, it's artificially produced by a pharmaceutical drug company, and this also goes and binds onto H2 receptors to produce the same or similar response of gastric acid release. But the pharmaceutical companies, when they're designing our exogenous bistabine, they can design it to be slightly stronger or weaker than histamine so that they can kind of like fine-tune it to produce the exact responses we want and need to fight off the condition or the disease that we're trying to go after. So what does strength actually mean though? What does it mean to say that this exogenous bistamine can be stronger than histamine? There's actually a few different aspects to strength. You have affinity, efficacy, and potency. Let's take a look at what all three of these terms mean and how they differ from each other. So before we look into our three measures of strength, we have to have a better understanding of the binding process of messenger molecules onto your cell's receptors. So the binding process of messenger molecules onto receptors is random, or a more formal term is stochastic. So basically, you have a cell, right, with, let's say, 10 receptors, and you have a bunch of messenger molecules outside, right? These messenger molecules are going to move around randomly in all directions. And randomly, stochastically, these messenger molecules may end up binding to your receptors. So they'll go over and they will bind onto your receptors. But they're not going to last there forever. After some time, they're going to leave your receptors and go elsewhere. And then other messenger molecules can come and take its place. So messenger molecules are moving around randomly or stochastically binding onto receptors, leaving receptors, and messenger molecules are taking each other's place. It's a big random process, a cycle of binding and leaving and moving around. So this creates some kind of balance. And it's important to understand these two terms. The process of a messenger molecule binding onto a receptor is called association, and the process of the messenger molecule leaving the receptor is called dissociation. Now, if you've taken chemistry, you're probably familiar with the concept of rate constants, represented by the letter K. So for example, you have KEQ, which is your equilibrium constants. You have Ka, which is your acid dissociation constants. You have Kp, which is like your equilibrium constant, but it's in terms of partial pressure units. So K is, a general unit for rate constants, and this applies for association and dissociation of messenger molecules onto receptors and off of receptors. So K on is your association rate constant, and it basically describes how readily or likely messenger molecules will bind onto receptors. So remember, like we said, messenger molecules, they move around randomly and can stochastically bind onto receptors. So the K on, it basically describes how likely it is for it to stochastically bind onto receptors. So let's look at an example, right? Here you have two messenger molecules, and let's assume that they're at equal concentration. And in both cases, you have a cell with an equal number of receptors. So as we said, these messenger molecules are going to move around randomly, stochastically, and stochastically they're going to happen to bind onto receptors and then eventually leave these receptors. But if messenger molecule A has a higher K-on constant as opposed to messenger B, which has a lower K-on constant, that means that messenger molecule A will more readily bind onto these receptors, more likely to bind onto them as opposed to messenger molecule B. Okay, so just like we have an association rate constant denoted by K on, we also have a dissociation rate constant denoted by K off. And this is the opposite. K off, or the dissociation rate constant, it basically indicates how readily messenger molecules are to leave or dissociate from your receptors. Higher K off means that a messenger molecule will dissociate from a receptor faster and more readily. So going back to our previous example, let's say that, so again, you have messenger molecule A and messenger molecule B, equal concentrations of both binding to same receptors of the same cell. And like we said before, let's say molecule A has a higher K on, but now let's also say that it has a higher K off. So the higher K on will mean that messenger molecule A will be more likely and more readily bind onto receptors as it moves around stochastically. But the higher K off means that it will also more readily and more likely leave these receptors faster. So its time bound to these receptors is short-lived. It's easier for it to bind, but it's also easier for it to leave. So now that we understand our association and dissociation rate constants, K on and K off, we can now understand the first of our three measures of strength. So the first measure of strength we're going to look at is called affinity. As the name suggests, affinity is the attraction that your messenger molecule or ligand or your drug has to a receptor. So it's how badly it wants to attract to it and stick to your receptor. And this depends on your K on and K off. Remember, K on is your association rate constant. It can be thought of as how readily your drug wants to bind to receptors, and your K off can be thought of as how readily your drug wants to leave receptors. So higher K on means it's more likely to bind, higher K off means it's more likely to leave. So these these are both imperative for affinity. Let's say a drug with a high affinity, right? It will likely have a high K-on and a low K-off. Why is this? Well, high K-on means the drug is more likely to go and bind onto receptors. So it's more likely to go and, stick onto them. And a low K-off means it's not going to want to leave these receptors as readily or as fast. So it's going to bind onto receptors easier and it's going to stay on these receptors for longer. Together they produce a high affinity. And then you have low K-on and high K-off. These characteristics will produce a drug with a low affinity. So low K-on means it's not going to want to go and bind onto receptors as quickly or readily, and high K-off means it's going to want to leave receptors faster. So it's not going to want to bind onto receptors, and when it does, it's going to want to leave faster. Both of those make a drug that is not going to want to stick onto receptors as much. Therefore, the drug will have a low affinity. Now, in reality, most messenger molecules, they have pretty similar association or K-on rate constants. What often differentiates between messenger molecules is the K-off constant, which is the dissociation rate constant. So some messenger molecules will have high K-off constants. In this case, let's say messenger molecule A has a high K-off constant. That means it will leave messenger molecules more quickly and more readily. On the other hand, if messenger molecule B has a lower K-off constant, it will be less likely and it will be slower to leave messenger molecules. So messenger molecule B with the lower K-off constant, it will be more likely to stick onto receptors for longer, and therefore messenger molecule B will have a higher affinity. So when pharmaceutical companies, they design their drugs, they can design them to have specific characteristics, and that includes affinity. So they can design drugs to have higher or lower K-on and K-off values to give them a desired affinity and make the drug as effective as possible. So now we know that affinity is a messenger molecule's ability to bind and stick onto receptors. But now let's look at the second measure of strength, which is efficacy. So efficacy it describes a messenger molecule's effectiveness at producing responses once it's bound to receptors. So it's how good it is at producing responses. You can think of this as a messenger molecule's brute strength. So how strong of responses can it produce? So going back to our old example, you have two messenger molecules, A and B, binding onto receptors and producing responses, but messenger molecule A has a higher efficacy compared to messenger molecule B. That means when it goes into the receptor and produces responses, these responses are going to be a lot stronger compared to the responses of messenger molecule B. That's what efficacy is, how good it is at producing responses, how strong these responses can be. Higher efficacy means stronger response. And what do we mean by stronger response? Well, it depends what kind of response we're talking about. If we're talking about muscle contraction, then a stronger response means more contraction, more muscle tension, a stronger contraction. If we're talking about, let's say, stimulating gastric acid release, then a stronger response would mean probably more gastric acid being released. So if you think about affinity as the ability for a messenger molecule to stick onto receptors, ability to stick, then you can think of efficacy as its ability to do responses. So affinity is ability to stick, stickiness, attraction. Efficacy is the ability to produce or do responses. And just like how drug companies can design drugs to have higher or lower affinities, they can also design drugs to have higher or lower efficacies. So now that we understand what affinity and efficacy are, we can now move on to learn about dose-response curves and eventually understand potency. So what are dose-response curves? They're graphs that help us to understand the relationship between the concentration or the dosage of your drug and the response levels of the cell where responses happen. So the relationship between dose and response, hence the name dose-response curve. Here's an example of your standard dose-response curve, and the shape that you see is characteristic with most dose-response curves. So when you have no concentration of your drug, it makes sense that you have no response. And then as you increase concentration, slowly response levels start to increase. Then as you can see, as you continue to increase concentrations, the response levels increase faster and faster until they shoot up, they spike up. And then As you continue to increase concentration, they plateau off again. Response levels stop increasing as quickly, and eventually it hits this maximum point where this is your maximal response. It cannot go any higher than this. So even if you add more concentration of your drug, no matter how much you add, this is your limits. The response levels will not go any higher than this. So remember what we just learned about efficacy. Efficacy is the ability for your messenger molecule to produce responses, how strong it can produce responses. So, because this is the maximum possible response that your drug can produce, we can call this the maximum efficacy, denoted by this term Emax. So let's say we had another drug with a higher maximal efficacy. It has the ability to produce a higher maximum response. Then the dose curve might look something like this. So the plateau at the end is at a much higher point because it has a higher Emax. The maximum response or maximum efficacy is higher as opposed to this dose response curve. Okay, so now we know that maximal response is Emax, which means maximum efficacy. It's a maximum possible response of your drug. Now let's look at something called the EC50. So EC50, it means half maximal effective concentration. So half maximal effective, basically it's saying half of your maximum efficacy. And here it says concentration. That's exactly what your EC50 is. It's the concentration of drug you need in order to produce a response that is half of your maximum efficacy. So, for example, in this graph, right, we've already established that this is your Emax, your max efficacy, your max possible response. And what is your max possible response? It is 5 millinewtons. So let's say this is the response that we're measuring is muscle contraction. So 5 millinewtons is the maximal possible response possible. Maximal response that is possible. So now for EC50, it's the concentration needed to produce a response that is half of your maximum. So what's half of 5? It's 2.5. And here is 2.5 on your graph. So what concentration do we need to produce a response of 2.5 millinewtons? Well, we can see where it lands on our dose response curve, and it lands right here. So we need a concentration of 5 millimolars of our drug in order to produce this specific response. And this response is half of our maximal efficacy. So therefore, that would make 5 millimolars our EC50. 5 millimolars is the concentration needed to produce this response, which is half of our maximal response. This is your EC50. Okay, so your EC50, right? It's the concentration needed for half of your maximal response or your maximal efficacy. Now with this, we can now go on to understand the third measure of strength. Remember, we talked about affinity and efficacy. Now we're going to focus on potency. So potency measures the relationship between a drug concentration and the response produced. So if you need a lot of concentration of drug in order to produce a response, that means your drug is weaker and less potent. Now, if you're able to get the same response, but with less concentration of your drug, then obviously your drug is stronger, and we call this more potent. So to review that again, let's say you're trying to get a very specific response of, 5 millinewtons. One drug is able to get that with a concentration of 1, and another drug is able to get that same response with a concentration of 10. The drug that's able to get the response with the lower concentration of 1 is a lot more potent because you're able to get the same response with a much lower concentration compared to the other drug, which needs 10 to get that same level of response. It's a lot weaker and less potent. So that's potency. And what's cool is that potency is inversely related to your EC50. If you have a lower EC50, because remember, what is EC50, right? It's the concentration needed in order to produce half of your max response. So in this case, half of your max response, we already said it's 2.5, so it would be along this line, right? Now, if you're able to get this response level with lower concentration of drug, So you have a lower EC50, then that would make your drug more potent because you're able to get a response with a lower concentration. So less EC50 equals more potent. On the other hand, if let's say you needed a greater concentration just to get this same level of response, then your drug would be less potent, because to get that same level of response, you need a higher concentration of drug. So higher EC50 means more concentration needed to get the same response. Therefore, your drug is less potent and weaker in the sense of potency. Okay, so I know I just dropped a lot of information and it can be a bit confusing, so hopefully this diagram can make things a little bit more clear. So here we have two dose response curves. The blue one represents messenger molecule A, and the green one represents messenger molecule B. So two different messenger molecules, and as you can see, they both have the same level of plateau, and that represents that they both have the same maximum possible response, the same maximum efficacy, and that maximum final response is 5. We're ignoring units just to make things simpler, so 5 is our maximum response. And here we have drawn our two EC50 values, because what's half of 5? It's 2.5, which comes around here, and so for messenger molecule A, in order to hit that EC50, in order to hit half of the total maximum response, so that's 2.5, it needs a concentration of 5. Whereas messenger molecule B needs a little bit more. It needs a concentration of 6. So here are your two EC50 values. Messenger molecule A, concentration is 5. Messenger molecule B, concentration is 6. And keep in mind that these are both producing the exact same level of response. They're both producing a response of 2.5. So now let me ask you guys this. Which one do you think is more potent? Remember, a more potent drug needs less of the drug to produce the same response. A less potent drug needs more of the drug to produce the same response. So in this case, in order to produce the same response, messenger molecule A is able to pull it off with less concentration, with only 5 instead of 6. So that would make A excuse me. That would make A the more potent drug, right? On the other hand, messenger molecule B, in order to get that same level of response, it needs a little bit more concentration. It needs 6. Therefore, it's not as strong. It's not as potent. So B is your less potent drug. And as we said before, EC50 is inversely related to potency. Your EC50 for A is 5, so it's less, and as a result, it's more potent. On the other hand, for B, it has a higher EC50 of 6, and this results in a lower potency. Alright, so we've gone through a bunch of new concepts and terms in this video, and I understand they can be very confusing. So before we go out and end the video, we're going to do a recap of everything we've learned. So, messenger molecules, also known as agonists or ligands, can go and bind to receptors on cells, or even inside cells, and produce responses in these cells, all sorts of responses. Now, these messenger molecules can be endogenous, meaning they're produced inside the body naturally, or exogenous, meaning they come from outside the body and are usually man-made by pharmaceutical companies. Now, the first measure of strength that we have is affinity. Affinity is basically attraction. It's how much the messenger molecule wants to bind onto receptors and how well it wants to stick onto them. So you can think of it as the attraction between messenger molecule and receptor. And it depends on your two rate constants, Kon, association rate constant, and Koff, dissociation rate constant. Higher Kon means it's more likely to bind. Higher Koff means it's faster to leave. So for a high affinity, you want a high Kon and low Koff. For a low affinity, you would have a low Kon and high Koff. So then you have efficacy, which is your ligand's ability to produce responses. So after your ligand comes and binds to receptors, if it has a higher efficacy, it'll be able to produce more response. If it has a lower efficacy, then maybe its responses will not be as high. And you can see in a dose response curve, which models a drug's concentration and its responses against each other on your x and your y axes, you can see that the response levels after a certain while, they plateau off. This is your E max, which is your maximum efficacy. No matter how much concentration of drug you add, the efficacy will not get any higher than this plateau, this value. And then you have your EC50, which is the concentration of drug needed to have a 50% response of your max efficacy. So this is your max efficacy. You take the half of that, and the concentration needed for that is your EC50. And from here, we can get the final measure of strength, which is potency. So potency, basically, if a drug is able to produce the same response with less concentration, it's stronger and more potent, whereas if a drug needs more concentration to make the same response, it's less potent. And one way to look at how much how much concentration is needed for a set response is to use this determined EC50 level. If you need more concentration for your EC50, then you have a higher EC50, so it's less potent. And if you need less concentration for your half maximal efficacy, then you have a lower EC50, and therefore your drug is more potent. So comparing one last time, affinity versus efficacy versus potency. Affinity is the ability for ligands to bind and stick onto receptors. It's the attraction between ligands and receptors. Efficacy is the ability for ligands to produce responses. And potency is how much concentration of the ligand is needed for a specific response. And one last thing to consider, you can think of affinity and efficacy as being directly related to the stuff that they measure, whereas potency is more so inversely related. And what I mean by this is, for affinity, right? If a messenger molecule has a better ability at sticking to receptors, it's better at sticking, it's able to stick, faster and more readily and stay on longer, then it has a higher affinity. So these two are directly related. For efficacy, same thing. If a messenger molecule is better at producing responses, it's able to produce higher, stronger responses, then it has a higher efficacy. But with potency, it's the other way around. If a messenger molecule needs a higher concentration to produce a response, then it's less potent. If a messenger molecule is able to produce a response with less concentration, then it's more potent. So you have to consider that. Like with potency, it's kind of the opposite. Less concentration needed means more potent. More concentration needed means less potent. And with that, I hope you guys are able to have a better understanding of the differences between our three measures of a messenger molecule's strength and power. And that just about wraps up our concepts of affinity, efficacy, potency, EC50, and dose response curves. I hope you guys found this video informative and useful and easy to understand. If there's anything you guys like, if you have any suggestions or want me to go over the thing again or make a video on something specific, please let me know down in the comments. I'm open to hear out any feedback and any ways that I can improve. In the next video, we're going to learn about antagonists, partial and inverse agonists, adding a bit more complexity to our current idea of agonists and messenger molecules. But until then, thank you guys again so much for watching. Take care. See y'all next time.